So let's just go ahead and start off with your background. Maybe tell us a little bit about yourself.
Sure. Yeah, I am a second year PhD student at UIUC, and I'm also part-time at Meta right now as a research science intern. And then I finished my undergrad at UVA around 2 years ago and worked at Meta and Palantir in the past. And I'm focused on a lot of research broadly revolving around world models, energy-based models, self-supervised learning, generative modeling, that type of stuff.
Awesome. So let's just go ahead and get started with your background in sort of computer science. Like, where did that sort of originate? How'd you get interested in AI research?
Yeah, so it was a long, drawn out path that I did not necessarily shoot for directly. So I'll give you a little bit of background was I did a lot of robotics in high school and middle school as well. And I really enjoyed robotics and I thought it was great, probably the coolest thing I ever did at that age. And then coming into college, I was like, oh, I want to do mechanical engineering because I really want to do robotics. I started doing mechanical engineering when I was at UVA and I found out I did not like it too much. So I switched to computer science because I had done some computer science classes in high school, and I found the computer science classes in college to be much more interesting, and I thought that I could do more with it. So I kind of continued on that track, and then eventually I stumbled upon AI, and I was like, wow, this is really cool. And it also kind of brought me full circle to the point where I was like, whoa, like this is very applicable to robotics, which I really like. So that brings me to where I am now, which is, I'm focused fully on AI, and I did my undergrad in CS. So
Awesome. So I guess like maybe tell us a little bit about your kind of research journey throughout undergrad, kind of what got you interested in like energy-based transformers during your PhD.
Yeah, great question. So to start off, I didn't really know what I was doing with AI research. So I started off with a small project on a Raspberry Pi, which was just like facial recognition. Uh, and this was kind of like a really just stupidly easy project. But that kind of planted the seeds for me being interested in AI. And I was like, well, like this is really cool. I really want to learn more and kind of grow. So I joined a lab called the Collaborative Robotics Lab at UVA. And my first project was actually not really related to what I'm doing at all right now, but I think planted the seeds for me to kind of start getting interested in it, which was developing a simulator for multimodal human interaction, which is pretty early at the time. So, for reference, this was around 2022. People weren't too interested in multimodal learning, but we were working on vision and language and kind of bridging the gap via simulated data. And I like this project, but eventually I came to the point where I was like, hey, I want to work on something that's much more kind of future facing if possible. So I was watching a lecture by Jan LeCun, and he started talking about energy-based models. And I remember hearing about this, and just for reference, feed-forward model, the way it works is you'll take as input X and you'll output some Y prediction. And an energy-based model actually learns like the compatibility between this X and the Y. So both X and Y are inputted, and it gives you a scalar energy. And I remember watching like 30 seconds of this lecture. I was eating breakfast and, I wasn't really paying attention, but I watched like 30 seconds and then I stopped it, went to class, was late. But I was thinking about it the whole time. I was like, wait, this makes so much more sense than a feed forward model. I don't know, for whatever reason, I just thought it was extremely intuitive. And I started thinking about it. And I spent several months thinking about it. And then eventually I was like, I want to work on this. And in my head, I was like, well, no one really knows what these things are and no one really uses them. So there has to be a lot of room to make them work because if they make sense intuitively, they should work empirically as well. So that kind of led me down this long, drawn out path, pursuing energy based modeling, and eventually focusing on kind of scalability and good algorithms for energy based models as well as architectures, hence the path to energy based transformers.
Awesome. And I guess kind of like looking forward, like now you're kind of a CS PhD student at Illinois, like, obviously energy-based transformers is a really exciting topic to work on. Like, what are some of the other topics more broadly that you're interested in kind of pursuing during your PhD?
Yeah, that is an interesting question. So, one of the broad topics that I'm interested in is world modeling, particularly for reasoning and planning. I think right now that there's a lot of focus in the field on LLMs, which is great for some reasons because LLMs are very useful. So, I use LLMs almost every day, and I think most people in our field do nowadays. I think the big challenge is that LLMs have kind of projected our field into like a mini local minima where they're very useful and they seem incredibly intelligent, but yet it's becoming clearer and clearer that they're not going to get us to the ultimate goal of the field, which is human level intelligence. At least this is what the field is tending towards, and it seems is the correct answer after kind of the past year and plateauing of foundation models. So in my eyes, the big trend or kind of focus that the field will focus on over the next 5 years is world models, particularly learning kind of a generative model that models some future states of the world given past states and is able to do that condition on different actions. And ideally, this allows you to have capabilities such as common sense and a causal understanding of different actions, reasoning, planning, all these nice characteristics. Um, One thing that I'm really focused on right now is making it possible to learn energy-based world models. So there's a great kind of overlap that can occur with energy-based models and world models, where if you learn a really good dynamics model or really good world model that understands what will happen in the future, given current actions, you can do zero-shot planning. And with energy-based models or energy-based world models, that becomes much easier. I'm happy to dive more into that if you'd like, but the general idea is that by just learning from an offline data set of trajectories, you can do zero shot planning to any goal state in any environment, would be the idea. And that's sort of the vision that I have for my PhD. That's what I'm working towards. But there's many roadblockers on the way to that. So, of course, representation is very important for world modeling, less important for language. So that's another thing that I'm focused on.
Awesome. So let's just go ahead and dive into kind of, I guess, your first paper in the kind of EBT world. Maybe tell us a little bit about your paper titled Energy-Based Transformers Are Scalable Learners and Thinkers. In particular, kind of like the motivation of the paper, which I guess you've already kind of highlighted, but maybe tell us a little bit about the inception, kind of tell us the story of how this paper sort of came about.
Yeah, the path to this paper was very nonlinear. So I actually started this paper out when I was like a third year undergrad, and I didn't know what I was doing back then. So I made many, many kind of mistakes exploring the research space. But it started out with just this hypothesis, which is, hey, current models are primarily feed forward. This does not make sense for many reasons. So I could give an example. There are certain problems that are computationally intractable for a feed-forward model to solve, but energy-based models can't solve it because they can dynamically allocate computation and kind of iteratively solve problems. Um, and to me, it just the core intuition behind this push for energy-based models is really just that, like, hey, these are a class of models that are inherently more powerful than feed-forward models. There is no doubt that they will eventually become widely used. The question is when and how. And that's kind of what I set the goal of the project to be, is to make these models usable and good. And energy-based models have historically, I would say, been both blessed and plagued by a couple of factors. So energy-based models actually used to be very popular. So back before deep learning kind of became super mainstream, Jeffrey Hinton was working on Boltzmann machines, which are energy-based models. And Jan LeCun and Joshua Benjo were also working on EBMs in different flavors. So the field has long had interest in energy-based models. But the big challenge that I've seen that I think has kind of plagued them is that there's been a lot of theoretical interest. So a lot of people are just saying like, hey, you can do this with an EBM, you can't do this with a feed-forward model, or hey, there's this beautiful training algorithm called contrasted divergence for energy-based models that you can't use for any other kind of flavor of model. But there's been less focus on just making these things work. And in my eyes, a lot of the most impactful work in our field has just been on making stuff scale and work. So if you look at the transformer, a lot of the foundational uh, kind of pieces that the transformer leverages were actually built out before the transformer came out. So differentiable memory lookup, or what we now call attention, was invented in a paper before transformers. Residual connections was popularized before transformers. Um, a lot of these kind of core ingredients were developed before the transformer came out. And one of the reasons the transformer paper really kind of is a seminal paper now is because it said, hey, I'm just going to make all this stuff work and scale pretty well. And of course, there are many other contributions. I think another great example of this philosophy of just like papers being very impactful that are more focused on just making stuff work and scale is the denoising diffusion probabilistic models paper, where diffusion models actually existed well before this paper came out. This paper really just said, hey, how can I make these things work, even if it's conceptually a little bit less elegant? So that's my focus for energy-based models, is saying, hey, these things look absolutely amazing theoretically, but people haven't really put in the effort to make them work practically. My goal is just to make them work practically so people can use them for everyday applications. And so eventually, we realize this goal of foundation models that are trained with energy minimization.
Awesome. Okay, cool. So just kind of like getting into maybe like a bit more of the weeds of the paper. Tell us a little bit about kind of the methods that you kind of use, like what did experiments look like, and maybe kind of some of the initial results.
Yeah, of course. Yeah, so I'll give a high level overview as to how energy based models work because I think that's something that's less commonly known in the field than other techniques. And then I'll go into the experiments we ran and our results. Um, so as I was kind of highlighting earlier, normal feed forward model, you have this input and you directly predict this output. Um, with energy based models, you have both the input and the output, and you give like a scalar energy that tells you, hey, how compatible is this input with this output? The big challenge with these models is training these models, right? So you might say, okay, that makes sense. My model just learns how compatible this X is with this Y, this text is with the future token, or this, video is with the next frame. But how do I actually train this model such that low energy, usually low energy corresponds to high probability. So low energy or energy is only low when these two inputs or this input and this output that are being passed in the model are compatible and high energy elsewhere. And that comes to the big challenge of energy-based models, which is like, what training approach do I use? We adopted a training approach that basically frames this as gradient descent. If you're familiar with sampling, it's broadly called Langevin dynamics. But the general idea is you use the gradient of this energy function to kind of uh, minimize the energy function, and then you can actually supervise this gradient instead of doing more theoretically or historically popular approaches like contrastive divergence that don't scale very well. So the TLDR is framing energy-based model training as an optimization problem and supervising the gradient of the energy function. Um, so that was one of the big kind of contributions this paper is looking at that and kind of comparing it to different approaches, at least intuitively. And then we did a lot of experiments. So we did experiments spanning language, video, and images. I'll talk broadly about the language experiments because I think that those are the most exciting because the field is very focused on language right now. We focused on autoregressive language models. So that is a model that is trained to, given previous text, predict a distribution over the next token. So if your text was the dog chased the distribution over the next word might be cat. And then frisbee would be also high probability. And then something like elephant would be low probability. And we train energy-based transformers or EBTs with that task, as well as just your standard GPT style causal decoder only model. And we got pretty good results. So generally the models are more data efficient. They scale better with higher batch sizes. We even got some pretty nice results with scaling laws. These results are still pretty early stages. So energy-based transformers are definitely more expensive, especially at this scale to train. But right now we're working on kind of making things less expensive as well as scaling things better to kind of reduce cost. So for reference, a lot of the models trained in the paper are 3 to 6x as expensive, at least theoretically. And then PyTorch does not implement HVPs, which you need to train these models very well. So it ends up being, 8 to 10x times more expensive in wall clock time, which is really challenging to work with. No one wants to use 10 GPUs instead of one GPU. So we're working on making things faster by improving the learning algorithm and improving the generative modeling approach. But yeah, we conducted a lot of experiments broadly as well as in video and with images, and we also got good results. We did some denoising experiments where we beat DITs. Um, yeah, that's a high level overview.
Awesome. So I guess like in the paper, you guys talk a little bit about some of the limitations, and obviously we'll get into kind of your follow-on work. Maybe from your perspective, we've talked about some of the pros of EBTs. What are your kind of thoughts on pros and cons?
Yeah, so right now there are many cons, and I'm pretty openly honest about these. The big one that I hinted at earlier was computational cost. Right now they're significantly more expensive to train, which is something that we're working on, and I believe that we'll make a lot of, or we have actually made a lot of headway on, and we'll be able to put out soon. Um, Another big challenge is training instability, and I spent a lot of time on this and trying to make it not an issue in the energy-based transformers paper, which is that traditionally energy-based models have been more expensive in terms of compute, but also more unstable. So you'll have many more loss spikes, which makes training a huge pain because not only do you wait longer to train, but then your loss diverges and your energy based model just becomes slop. And you really don't want that when you're training models, especially at larger scale when this loss instability issue becomes exacerbated. So, one thing we spent a lot of time on and that I have some interesting insight on is just generally making energy based model training stable. So that's one big challenge. Another big challenge is we never scaled models beyond 1 billion parameters. And it is the case that sometimes what you'll see is that certain approaches look very good at small scale when you're at, less than 500 million parameters. But the second you go beyond 7B parameters, certain approaches look worse, or you need different tricks to make them better. And I think that this is something that we'll have to see if we need for these energy-based transformers.
Awesome. Yeah, I think we can go ahead and move on to your next paper, which is obviously also super exciting. I think this paper is titled EBT Policy, Energy Unlocks Emergent Physical Reasoning Capabilities. So this was, collaboration with Travis and UT as well. Maybe tell us a little bit about kind of some of this work.
Yeah, so this is mostly a follow-up paper to the energy-based transformers paper, where we focus on a specific application of energy-based transformers. And to give a little bit of background on this paper, we were focused on an application that diffusion has become very popular for, which is behavior cloning. So there's this paper called Diffusion Policy that came out, I believe, 2 or 3 years ago. It's kind of become the seminal work in behavior cloning. So behavior cloning is where you have expert trajectories, you have some labeled data about what to do in different situations, and you want to basically employ supervised learning to copy these expert trajectories and then hopefully generalize to a new environment. And diffusion policy has become very popular for that, mostly because it has had great generalization compared to other existing approaches, such as autoregressive models or um, an old paper on implicit behavior cloning with contrastive energy-based models. We basically asked the question in this paper of, hey, how can we improve current behavior cloning papers or works with these energy-based transformers, which have been shown to be pretty competitive with diffusion models, especially on some toy image tasks that we had in the EBT paper. And we kind of trained them for behavior cloning in both the real world as well as simulated tasks. And we generally saw very, very good results. So EBTs were converging faster during training, needing less than half the amount of data or training time. And then also we saw that EBTs were able to denoise faster at inference. So diffusion models often need like 10 to 20x denoising steps, which is really hard to work with because it takes a while to do. With these EBTs, we were able to use like just 2 or 3 denoising steps at times. And then kind of the most exciting thing that we saw, the two most exciting capabilities we saw were things that haven't really been observed in behavior cloning in the past, which is one, emergent retry behavior, and then two, accurate uncertainty estimates. So the reason I say this is because emergent retry behavior is perhaps the most challenging problem in all of behavior cloning. So standard supervised behavior cloning, where you're just copying predictions for different actions given states, tends to struggle with this problem where, let's say you've been trained on expert trajectories and your trajectories go like this, right? But your model makes a little bit of error, so it deviates off the path a little bit. Usually, once you start to deviate off this path, your neural network will be in a region that it has never been trained on. It will continue to deviate more and more and more. So rather than kind of converging back to the path, it deviates. And this is broadly, referred to as a problem called exposure bias. There are many works that try and reduce this, and diffusion models, although they suffer less from this in behavior cloning, they still do suffer from this problem. With EBTs, we really saw that they're able to avoid a lot of this problem because they are able to do generative modeling end to end. So instead of having this diffusion process where you model just a subset of the steps of denoising, and then at inference time, you kind of do all the steps. So training versus inference is different. Training is one step, inference is all the many steps. With energy-based models, you do every single step during training and then every single step during inference. And the big benefit of this is now you're actually learning your generative model end to end. So there's less exposure bias from generative modeling. Now, the big challenge comes from, hey, how can I make this approach stable and how can I make this scalable? And that's where EBT's really helped out is, we spent a lot of time making the approach scalable and stable. So we kind of had a great recipe for being able to do end-to-end generative modeling while also doing that in a stable and scalable way. And this allowed us to do stuff like, or not allowed us, allowed the model to do stuff like emergent retry behavior, where it deviates from the path. So let's say it's, trying to place this water bottle on my computer. It might deviate from the path and get in a region where it's never been trained on, but yet it's able to position the water bottle back to the path that it was trained on. And that's because of this explicit energy minimization, which allows you to kind of have your model know when it's uncertain because it has high energy, and then pull the actions back towards a more simple trajectory that it's been trained on.
Awesome. Great. So I guess like kind of moving forward, you spent some time working on both, just energy-based transformers as well as kind of this more recent paper, EBT policy. We talked a little bit about kind of your trajectory and kind of interest in EBTs. So I guess maybe more broadly, let's now kind of talk about some of your time in industry. So as you kind of mentioned, you're a research scientist intern at Meta AI. Even before that, you spent some time at Palantir as an intern as well. Kind of how do you sort of see kind of the future of industry when it comes to EBTs? Do you think this is something that can be largely adopted? I mean, theoretically, some, sort of companies might be able to kind of afford, the computational overhead and kind of more expensive sort of costs. Like, do you think this is something that can happen? What do you kind of see as the roadblocks?
Yeah, great question. So before I answer that question, I'm going to give a little bit of philosophy, which is the general trend of our field. And our field has been a field that very much leverages computation. So it used to be that people didn't care about neural networks. People cared about statistical learning approaches. And as compute has grown more and more, people's interest in neural networks grew. And then eventually, neural networks became state of the art at everything. In vision, convolutional neural networks used to be the standard. Vision transformers are more expensive than convolutional neural networks or CNNs, but now vision transformers are used almost exclusively because they tend to scale better. There are many other instances of this general trend, which I'm hinting at, which is that as compute grows more and more, people tend to use approaches that are more compute hungry and that scale or generalize better.
Mhm.
This is the general trend that I believe our field is going in with energy-based transformers, which is that, hey, I see these models, they're, maybe 3x, maybe 6x, if you want, maybe even 20x more expensive if you're not careful, right? But as compute grows more and more, we will have 10x and then 100x and then 1000x more compute. We will be able to afford these more expensive approaches more and more, right? So there's almost always this trade-off between using more compute and then scaling or generalizing better.
Mhm.
And that's really where I see these energy-based transformers going in industry is sure, in the next 6 months or a year, people might say, way too expensive, I don't care about this. But as industry goes more and more towards just leveraging more compute, which is already happening with these massive pre-training runs, and now with reinforcement learning for post-training, people are spending almost as much compute on RL as they are on pre-training. It's coming to the point where people are like, hey, it might be worth it to basically trade off 3 to 6x more compute to allow my model to be able to reason dynamically. That's what energy-based models allow you to do. So that's really where I see industry going in the next kind of 2 to 5 years. It's hard to predict the exact timeline, but 2 to 5 years is transitioning more towards energy-based models instead of just pure feed-forward models because we have more compute and because that added generalization that energy-based models often allow for is worth the extra compute. So that is the general belief. The question is, will there be other approaches that people use that generalize better than energy-based models and that also leverage computation better? Or will feed-forward models tend to kind of still overcome this with some other breakthroughs, it's difficult to know. But my vision, and I think the vision that is, of course, correct, is the one where energy-based models tend to become more and more used because of this computation growth over time.
Mhm. Awesome. I guess like this is obviously a super basic question, but energy-based models are kind of a larger family of models, and EBTs are almost kind of like a subset of energy-based models in general. Is there a reason why you guys specifically picked EBTs? I guess maybe transformers are kind of the mainstream thing these days, but are you guys thinking about maybe energy-based other types of models, or like what was that thought process?
Yeah, great question. This is something that people ask a lot after we put out the paper, and 100%. I don't necessarily believe that the transformer is this optimal architecture, which has kind of become more widely believed nowadays. Of course, there's still some people working on other architectures, but none have proved themselves against transformers yet. Um, the biggest reason we chose transformers for this paper was because they are known to scale very well, especially on modern hardware. I definitely believe that as time goes on more and more, and other architectures hopefully become more dominant, we will see, energy-based RNNs or energy-based other architectures take over. I think part of the reason we called it energy-based transformers was, of course, embodying this transformer mindset and this transformer architecture that we used, but also a deeper mindset, which is this belief that, hey, energy-based models are this theoretically beautiful thing that has great capacity, but has never really been realized. What's the best philosophy to actually make them just scale well and be usable? And that's kind of the transformer mindset in my mind, which is just an architecture that scales very well, is very good empirically, uses compute very well. So I would say it's both a architecture thing as well as a philosophical name.
Mhm. Awesome. I guess like another big trend that we see these days is obviously RL, which is, kind of everywhere these days. As we know, like, OpenAI had, for instance, O1, which is kind of like their RL thing that they had. And, as you have kind of hinted at, you've worked on kind of EBTs, which, maybe have some advantages and some disadvantages. Just kind of curious, like, how do you guys kind of think about, EBTs versus RL? Is there any kind of intersection that you see in the future? What are your thoughts there?
Yeah. So right now, I would say that reasoning via energy minimization, which is kind of what EBTs do,
Mm-hmm.
is sort of a disjoint angle from reasoning via RL. So they're actually both compatible, mutually compatible. RL
Mm-hmm.
is kind of in this direction where you do it during pre-training, sorry, post-training.
Mm-hmm.
Energy-based transformers are more of like a just unsupervised architecture that allows you to do reasoning. RL relies on human labels and
Mm-hmm.
rewards.
Mm-hmm.
Energy-based transformers are able to learn reasoning directly from unsupervised learning.
Mm-hmm.
So they're sort of different angles, and I think in the short term, we will see both of them used. So
Mm-hmm.
you'll see energy-based transformers used for the added reasoning. I say short term, but I mean more like 2 to 5 year range, where they're used more for reasoning from unsupervised learning. But then, of course, people still want this great kind of post-training effect that RL has for reasoning, and people will use RL with energy-based transformers. So they're mutually compatible. Um, Sort of a spicy opinion that I have is that in the long run, we really won't see this big difference between pre-training and post-training.
Mm-hmm.
So with us humans, there's no pre-training versus post-training. You're always just training. Same thing with inference and training, actually. There's no like inference versus training. You're always doing inference and you're always training. They're pretty much one and the same. You use inference to train. So I think both of these are sort of challenges that we're faced with modern architectures, which is that they have such different behavior during pre-training or during training versus inference, and
Mm-hmm.
during pre-training versus post-training. And broadly, we need to figure out how to make it so that models are able to not have this two-stage or three-stage approach now with mid-training, and just be able to continuously learn, continuously use the same training and learning algorithm, no matter what. And that is sort of a very open question right now. But I think that people will start to focus on as people start to realize that post training is very much data hungry and involves a lot of human labels, and because of that, doesn't scale very well. So,
Mm-hmm. Awesome. So I guess kind of like earlier, you kind of hinted at maybe, your very first time working on kind of EBTs and kind of exploring the field. You were a third year, I guess at UVA. And you kind of mentioned that you didn't quite know what you were doing, but as you kind of spent more time working on it, throughout your fourth year, and then getting to kind of Illinois for your PhD, you kind of maybe started to learn how to do research more effectively. So, a lot of people in the audience are probably undergrads that are interested in research, but probably more likely grad students that actually might even be early on in their grad, student journey. What are, it seems like you've learned a lot about research, in particular for EBTs, but maybe like more generalizable takeaways. Do you have any, like, what does good research look like? What have you learned?
Yeah. So there's lots of advice that I have.
Yeah.
It's difficult to distill all of it. There's a couple different philosophical points that I try and stick to that I think have been helpful. One is so make mistakes and try and make mistakes quickly and try and learn as quickly as you can. So I think a lot of people have this mindset where they're just fixed in terms of their capability. They're like, I'm as good as I need to be. I just need to get as much done as possible. Just push out all the work I can. And I think that they lack this long-term goal of just becoming a better researcher. I think that especially undergrads, especially first or second, or even PhD students who are close to graduating, should still focus on just growing as much as they can. Just learn as much as you can. Continue to develop your intuition on what works, what doesn't work, as well as your research vision for the future. And I think that this nonstop mentality of growth is probably the most important. Um, Another thing is research philosophy. So I think especially right now, where we are at probably one of the biggest exploitation phases. So there's always this exploration, exploitation trade-off, both in RL as well as in science. Right now, we're in very much an exploitation phase with LLMs. I think people are starting to ask the question again of, hey, are LLMs going to get us to human level intelligence, or do we need other approaches? And I think now is really the time where people should start to ask that question more and more and develop research ideas that are very OD or crazy or far away from the modern LLM architectures. Um, so I would say ask the very, very big and deep questions. Don't focus on just boosting your resume or getting a ton of citations on Google Scholar. Focus on asking very, very good questions, questions that really help you understand deeply what is happening. And I think that almost always works better in the long run, both for your own good in terms of growth and understanding of intelligence, as well as for having long lasting impact on the field. So let's see if I can come up with a third point that is very important that I do. Oh, get a very good mentor. Mentors make a big difference. I did a lot of stuff solo. I did have a mentor at some point, but I also made a lot of mistakes on my own, and I wasted a lot of time. Not wasted, but I learned, and perhaps wasn't as productive as I could have been. So I would say get a mentor who really cares about your growth, and you can tell cares about your growth, and spend as much time as you can with them, getting constructive feedback to improve as quickly as you can. I think that this is really key, and oftentimes mentors make the big difference between growing slowly and just becoming an amazing researcher. So I would say focus on surrounding yourself with people who can help you improve very quickly.
Awesome. And you kind of hinted at, there were maybe some things that you learned, or maybe some time that maybe was a little bit wasted, but you kind of learned from. Like what are kind of some of the, maybe give us an example of kind of a point in time where you wasted a lot of time doing something, but maybe, with advice you could have done it differently.
Yeah, great question. So there was okay, so I'll dive a little bit into my philosophy on research before I answer this question. So I think that a lot of times to do the best research, you actually need to be a little bit ignorant, a lot stubborn, and a little bit clueless. And that might sound crazy. Like, who in the hell should be ignorant and clueless? Those are probably the, biggest opposite of the advice you've ever heard of. But the reason I say that is because I think if you read the same things that everyone else does, and you know all the exact same details, and you're very much caught up with every single thing that's going on in a field, you actually reduce creativity. So there's this point where you read so much and you know so much that I actually think you become less creative.
Hmm.
Um, and I think that one of the key problems that people have is they just read everything and they kind of try and understand everything deeply. And before they do a project, they read up on everything that already exists. And it's great because they have so much knowledge, but it's also terrible because they've locked themselves into the mindset that everyone else in the field has. So I think that there's always this trade-off between how much do I have in terms of knowledge before starting a new idea versus, how much have I learned from other people? And there's a balance. Of course, if you know nothing, you're going to make progress extremely slowly. So if I didn't know what a neural network was before I had started to work with EBTs, it would be impossible for me to succeed. I think at that point, I did not know enough to be able to succeed, so I probably should have read more papers. But the reason I'm saying this is because I think there's also a balance where if you read too much and you know everything that already exists, you'll say, "Oh, this idea is going to fail, and this one's already been done, and this one isn't created." So I think that there's really a fine balance between knowing enough and also using cluelessness and what hopefully leads to creativity to your own benefit.
Awesome. All right. Well, without further ado, thank you so much for coming on the podcast.
Thank you for having me.